Hello, this is Dr. Nair with the next video on Chapter 4, cyclohexanes. And in this video, we will be talking about conformations of mono and di-substituted cyclohexanes. But let's do a quick review of how the different conformations of cyclohexane are drawn. If you recall the previous video, we had talked about the most stable conformation of cyclohexane, which is called as a chair conformation. Okay, and it is drawn in the form which looks almost like a chair. Okay, so let's redraw that. This is a cyclohexane, and this is the chair conformation of cyclohexane. So if you look, this is the head part of the chair, and this is the foot part of the chair. Okay, all right, and then at each carbon atom on the cyclohexane, we have an axial hydrogen and an equatorial hydrogen. Okay? Axial hydrogens are perpendicular to the ring, and equatorial hydrogens, which are represented in blue, are pointing towards the equator of the ring. Okay? So let's redraw that in a different slide. So here we have the cyclohexane drawn as a chair conformer. And I will put all the axial hydrogens in red color. So we have one, this carbon atom. All the axial has to be perpendicular to the ring. Here we have the 6 axial hydrogen atoms. The equatorial ones are the ones that point towards the equator. So the way we will draw is, if this hydrogen is pointing up, and here we have the equatorial pointing down. Here the pink hydrogen is pointing down axial, so your equatorial will point up. Okay? Here the hydrogen is pointing down, so your equatorial is pointing up. Here the equatorial is pointing down. Here it will be up, and here it will be down. Okay, so every carbon atom, if you look, has 2 hydrogens. We go back to the structure here. You can clearly see that at every carbon atom you have 2 hydrogens, one which is pointing on the top part of the plane and the other which is towards the bottom. Okay? And at the same time you also have one equatorial and one axial. So once that you have learned to draw that, you can move on to the flip structure. Okay? So chair conformer of cyclohexane can readily interconvert into a flip form, right? So they keep on doing this. There's a small difference in energy between those two, and they can keep on flipping from one form to the other. And while doing that, whatever group was on the axial will now become equatorial, and whatever equatorial will become axial. Okay, so let's practice doing the flip form. Here I'm going to draw the cyclohexane molecule, and then we'll draw the flip form. Okay? So here we have the cyclohexane with, say, this is my axial hydrogen pointing up, and I have the equatorial hydrogen pointing down. Okay, and I'm going to tag this carbon atom which has the 2 hydrogen atoms with a, say, green color here. Okay, now see what happens when I do the flip. I'm not drawing all the hydrogens because I wanted you to see how the substituents at one carbon atom, or the hydrogen at one carbon atom, the one that is axial changes to equatorial, and the equatorial becomes axial. Okay? So while drawing the flip, you have to make sure that you are moving this down, the green carbon down, and say if I mark this one as a purple, then the purple will go up. That's how the flip is drawn. Flip structure is drawn. Okay? So when you draw that, this is what it will look like. The flip structure. I'll put back my colored carbons. This is my green carbon now because you pulled it down, and then my purple carbon is over here. Okay, and then when I draw the hydrogens, the hydrogen that was pointing up, okay, so this axial hydrogen will now become equatorial. Okay, so that hydrogen will become equatorial, and the blue hydrogen, which was equatorial, will now become axial. Okay, the other thing that you need to understand is that even after doing the flip, okay, so you did the ring flip, but a pink hydrogen which was pointing up will still remain up. Okay, so axial up, now it is equatorial up. This was equatorial down, the blue hydrogen, that's now axial down. So whatever was up remains up even after the flip. Whatever was down remains down. What changes is axial becomes equatorial and equatorial becomes axial. Okay, so this is important when we do the flip structures. A quick learning check at this point. If you're asked what are the different types of strain in cycloalkanes, there are three main types of strain. Angled strain, because if you recall, they are deviating from normal tetrahedral angles even though every carbon atom is sp3 hybridized. So that causes angle strain. Torsional strain is when the eclipsing of bonds happen on neighboring atoms, which in case of cyclohexane, it's almost zero. And steric strain is when bigger atoms come close to each other and there is crowding that causes repulsive interactions, and that is called a steric strain. Alright, so now we are putting substituents on the cyclohexane and then try to see if we can draw the chair structure and its flip structure. Okay, so there are three examples given. So they will all have similar ways of drawing. So let's pick one of them. Okay, so we have a cyclohexane with a CH3 group attached to it. So let's go ahead and draw the given molecule. So this is the given molecule and it's asking you draw the chair structure. So the question is draw the chair and its flip form. Okay, so draw the chair conformal and also its flip form. Okay, so we'll start by drawing the chair conformer. Here is my one of the chair conformers. Okay, now this CH3 you can place it anywhere in the molecule because it's all every carbon atom is similar, same. Okay, and since it is not telling you whether it is up or down, you can choose whether you want it to be up or down. Okay, so I'm going to put it up here. The way I drew it is now it looks like an axial. Okay? So every carbon atom will have an axial and an equatorial, and you can choose which position you want because the question is not is giving you the freedom to choose whether axial or equatorial or any carbon atom. Okay, all right. So you put it axial up, and then when I draw the flip form of it, again put a red color here on the carbon atom, so that you can track where the carbon atom goes when I do the flip. Okay, so we put a arrow like this for showing the flip structure. So in the flip structure, your pink hydrogen atom is going to be here. Okay, and the pink carbon atom is going to be here, and then the CH3 that was axial, remember in a flip it will become equatorial, but it was pointing up, so you will still have to point it up, but only thing you will change it is that it becomes equatorial. So this is axial up, now it becomes equatorial up. Okay, all right, and it will be similar to the other molecules also. See, these are the answers for it. You could have chosen any point for putting the CH3 group. So here is a CH3 after the flip, equatorial, equatorial becomes axial. But it was pointing up, it still points up. That is important. Here the second extra example was for the OH. Here OH is equatorial up, it becomes axial but still pointing up. Here bromine was equatorial up, same thing, bromine is axial. Okay. All right, I want to give you one more example where in case the it's given to you in the question whether the substituent is pointing up or down. Okay, so for example, if you had a structure like this where it's given to you with a wedged bond. So wedged bond means coming out or pointing up. Okay, so here if say again I have a CH3, but it's already giving it to you that using this wedge bond, which means that it is pointing up, right? So in that case, you will have to make sure that your CH3 is pointing up. It's not telling you whether it is axial or equatorial, that you can choose, but what you have to keep in mind is that it has to be up, right? So this could be one way of drawing because now it's pointing up, okay? Or you could have taken a position where it has to be equatorial, right? So say for example this here, this is also correct because see here it's pointing up. It doesn't matter if it is axial or equatorial as long as it is pointing up because you are given a wedge structure. If you were given a dash structure like this, say with an OH, okay, I'm just changing the group here, and you're asked to draw a chair conformer of it, again you have the freedom to choose which carbon atom. Any carbon atom can be chosen, but what you have to keep in mind that the OH has to point down. Okay, this is telling you this OH is down, so you have to choose those positions on the carbon atoms where the OH has to look down. Okay, can you choose this position? You can, but you cannot make it axial. You have to make it equatorial because then only it will point down. If you or you could have chosen the carbon next to it, this carbon here, okay? But now since the OH has to be down, as the question says, you are forced to choose the axial. You cannot do the equatorial. Okay, so make sure that you remember that on every carbon atom on the chair structure, there is one up, then there is a down, down, up, and down and up axial positions. Okay, similarly, the equatorial positions on every carbon atom, you will have one pointing down, then the next one pointing up, the next one is pointing down, up, down, and up. Okay, so these positions are fixed. If you decide to choose any of the carbon atoms and you want to make sure that the substituent is either up or down, you have to carefully choose which carbon atoms will show you the down bond and the up bond. Okay, all right, as we practice more, I think you will get the idea of how to draw this. Okay. Now let's talk about the stability of monosubstituted cyclohexanes. So cyclohexane rings rapidly flip between chair conformers at room temperature, as we saw that. But both the conformers may not be equally stable. Okay, one conformer is more stable than the other, and the conformer that is more stable is always going to be the one where your substituent is on the equatorial position, and it is actually favorable by 7.6 kilojoules per mole, right? So in this slide you can see that there is a methyl cyclohexane. One is in the axial position, you did the flip and you got the equatorial position. Okay, and you can see that the arrow is drawn with the longer arrow towards the more stable conformer, and this more stable conformer is where the CH3 is going to be in the equatorial. So the reason why this happens is because of what is called as a 1,3 diaxial interaction. When the CH3 group is in the axial position, like in this model shown here, this is the green CH3 group, you can see that it has interactions with hydrogens that are axial to it at the 1 and 3rd position. Okay? Whereas when it is in the equatorial, those kind of interactions are absent because it's away from any of the other hydrogen atoms. Okay? So let me redraw this in a different slide. Okay. So here I have, we'll use the same example. Okay. So a methyl cyclohexane. So we have this as a methyl cyclohexane, and we know that there are two conformers of it. One is the chair conformer and the other is the flip conformer. Okay, the flip, when you flip that. So let's draw the first conformer, chair conformer, which looks like this. And again, I'm going to choose any CH3. So let me choose this one, but now my CH3 is actually axial. Okay. So what happens when this is axial is that there are the hydrogen atoms that are present on these carbon atoms. Okay, so there are hydrogens here, and then there is a hydrogen here. Okay? So this we call it as 1,3 position with respect to each other. So this is 1, 2, 3. Okay, so that these are the 1,3 hydrogen atoms. They actually interact with this CH3. And this is called as 1,3 diaxial interaction, which brings the energy of this conformer a little higher than its flip conformer. So when you flip it, you get the conformer which looks like this. And again, if I tag this carbon atom with a, say, green color, the green carbon atom is now here. Okay, so what you did was you moved this down and moved this up. So when you do that, you have your CH3 group in an equatorial position, because once you flip, the axial becomes equatorial. But whatever remains up still remains up. So CH3 was up, and here it is still pointing up. But it is free of any of those diaxial interaction because the hydrogens are away from it, and this is in the equatorial position. So no 1,3 diaxial interaction. As a result of which, this flip conformer is more stable than this one, which is less stable because of that interaction between the hydrogens that are at the 1 and 3rd position with respect to each other. Okay? So in a mono-substituted cyclohexane, always the equatorial conformer where the substituent is in the equatorial position is more stable than the axial. Okay, so equatorial more stable than axial. Okay, this is in case of mono-substituted. That means one substitution that is present. However, when we before I move to the disubstituted, see, these are some of the groups which can have the 1,3 diaxial strain, and smaller the group, less is the diaxial strain. Bigger groups have more diaxial strain. Like for example, look at this. This is a T-butyl group. A T-butyl group looks like this. So I will draw a cyclohexane here, where you have, instead of that methyl group, you have a tertiary butyl group. This is what the tertiary butyl group will look like. Okay, so you have a carbon with CH3, CH3, and CH3. So look at that. This is such a large group. So the interaction of these hydrogen atoms, this will be much larger. So that's why, see, it's 11.4 kilojoules per mole. But if this was a small atom like a fluorine, then the interaction would be much less, but it will still have a 1,3 diaxial interaction. Now the next part is regarding conformation of di-substituted cyclohexanes. Now in case of di-substituted cyclohexane, you have more than one isomer present, correct? Because you will have a you can have the two substituents at the 1 and 2 position, and they can be cis to each other or trans to each other. You can have 1,3 substituent present in 1 and 3rd position, and again you can have cis and trans, and then again 1,4 cis and trans. So you will have more isomers in this case, so we have to look into each one of them separately. So here we are looking at a 1 and 2 position, right? So let's redraw that. So now we are looking at di-substituted cyclohexanes. So again, let's keep it to methyl group 2. Simpler. You have two methyl groups. Okay, that's why di-substitution. Now, when you have di-substitution, and they can be at the 1 and 2 position. So here we have 1, 2 dimethyl cyclohexane. Now this can be drawn as cis or trans. So the way we can draw the cis is by keeping both the groups up or both the groups down. Okay, so I have the CH3 here and a CH3 here, or I can do the trans, okay, where I can have one of them pointing up and the other pointing down. This is my cis conformer and this is my trans conformer. So when I draw the cis conformer as a chair structure, I have both of them pointing up. So this is up, and this other CH3 is also up, and if I decide to choose this carbon atom, the only way I can make it up is an equatorial, right? So I have an axial CH3 and I have an equatorial CH3. Right? Now when I do the flip of this, what will happen? This will go down and this carbon will move up, right? So let's again tag them. Let's put a red color here and a blue color here. Okay. So when I flip it, this is what it's going to look like. Where my blue carbon atom is now here because I moved it up, and my red carbon atom is going to be here. Okay, now let's put back the substituents. At the red, I had a methyl group which was pointing up. Now it becomes axial and it will still be up. So this was my 1 and this is my 2. So if this is my 1 here, then the 2 is here. Okay, and the equatorial, which was pointing up, will now become axial, pointing up. Okay, so in case of a cis conformation, actually the two conformers are equally stable. Equally stable when we are looking at a 1,2 dimethyl cis conformer. Okay, so this what we did right now is the cis conformer. And they look equally stable, right? See, one axial, one equatorial. Here again, one equatorial, one axial, so both of them are equally stable. But let's try to do the trans and see if we get the same answer. So in a trans conformer, the two methyl groups, one would be up and the other will be down. Okay, and this is again 1,2 dimethyl cyclohexane. Right? And this is particularly the trans conformer, as we did in the previous slide. So when I draw this as a chair conformer, to make it trans, one has to be up and one has to be down. And here again, you can choose any two positions which are right next to each other. Right? I will tag them with a blue color as we did before, and we have a, say, green on this carbon atom. Okay? Now when I flip it, I have my green here now. Structure here. Okay, now let's go back and put the substituent. So we need it to be trans, so I'm going to put the one up here, right? And the other has to be down, right? See, down. The only way I can put the other down is by using my axial. So I have an axial up and an axial down. Now it looks like trans, okay? The two CH3 groups are at the opposite faces, so it's trans. Now when I flip it, this CH3 will go up and this CH3 will go down. This will be up equatorial and this will be down equatorial. Equatorial and equatorial. Now there is a difference in stability, because we know that whenever groups are in equatorial position, they are more stable than when they are in axial, because when they are in axial, remember that 1,3 diaxial interaction will happen. So in this case, this is my more stable conformer, because we have both the groups in equatorial position. So this way you can try out with the 1,3 dimethyl cyclohexane cis and trans and 1,4 dimethyl cyclohexane cis and trans. Okay, these are again some more examples which you can try to see if this helps you to understand this concept much more clearly. All right, we can pick one out of the four, and I'm going to do the C part because we did not do the 1,4 so far, right? So let's do cis 1-T-butyl 4-chlorocyclohexane. Okay. So to draw that to the normal planar structure would be like this. It is cis, so both the groups have to be on the same surface. It's T-butyl, so that's the T-butyl, and then at the fourth position you have a chloro group. So this is 1, 2, 3, 4, and that's the planar structure. And when you draw the chair conformer, Cl has to, in this case our Cl is pointing up, so let's put this here up, and then the T-butyl is also pointing up because it's a cis structure, right? So we have to, this is my 1 carbon, 2, 3, 4, right? So we just number it 1, 2, 3, 4. Here I have 1, 2, 3, and 4. So at the fourth one and the fourth position, the T-butyl group and the chloro group are cis to each other. Now when I flip it, so I have one axial and one equatorial, right? Now when I flip it, the carbon containing the chlorine is over here, so that will become equatorial. The carbon containing the T-butyl group is over here, and that will become axial. Okay, so now which one would be more stable? This is more stable because here the bigger group, which is my T-butyl group, is in the equatorial position, and that is more preferred than having the T-butyl group in the axial position. Okay. So we'll circle this and say, this is ask you which one is of lower energy. So lower energy means more stable. So this is the one with the lower energy. Sorry, must it have. Okay. Now this one, it is the this one is the one with the lower energy, the one which is more stable and lower energy. Okay. So I would like to you to practice the other examples that are given here, and this is how we decide on the stability of mono-substituted and di-substituted cycloalkanes. Okay, we'll see you guys in the next video.